In this episode, we're going to make public key infrastructure, PKI, feel like a real-world system instead of a mysterious acronym that only shows up during certificate errors. Most beginners first meet PKI when a browser throws a warning, a secure website fails to load, or an application complains that it cannot verify a server's identity. Under the hood, PKI is the machinery that helps devices decide who to trust when they connect, exchange sensitive information, or rely on digital signatures. It is not magic, and it is not perfect, but it is a practical solution to a hard problem, establishing trust at internet scale without everyone personally meeting each other first. To understand it well, you need to see how certificates represent identity, how trust chains are built, how validation works in normal conditions, and why revocation often fails to behave the way people assume it does. Once you have that mental model, certificate warnings stop feeling random, and you can reason about what went wrong and what the real risk is. A good first step is separating three ideas that are easy to mix up: encryption, identity, and trust. Encryption is about keeping content secret from eavesdroppers, but identity is about knowing who you are talking to, and trust is about deciding whether you accept that identity claim. PKI primarily lives in the identity and trust space, even though it often appears together with encrypted connections. When you connect to a service securely, you usually want both confidentiality and assurance that the service is the one you intended to reach, not an imposter sitting in the middle. PKI provides a way for the service to present a proof-like object called a certificate, and for your device to validate that certificate using a set of trust rules and known trusted issuers. The important beginner takeaway is that PKI is less about hiding data and more about establishing and verifying identity claims that enable secure communication. If identity is wrong, encryption can still happen, but it may be protecting a conversation with the wrong party. A certificate is essentially a signed statement that binds a public key to an identity, along with supporting metadata that describes how that binding should be used. The identity might be a domain name, an organization, a person, or a device, depending on the type of certificate and the environment. The public key inside the certificate is not secret, but it becomes useful because the certificate asserts that this particular public key belongs to this particular identity, and that assertion is backed by a signature from an issuer. The certificate also includes details that matter in practice, like validity dates, constraints on usage, and identifiers that help systems manage the certificate over time. For beginners, it helps to think of a certificate like an ID card that contains both a name and a cryptographic component that can be used to prove control. The cryptographic signature on the certificate is what gives it weight, because it shows that a trusted party vouched for the binding. The role of the issuer is central, and this is where certificate authority, CA, comes in. A CA is an entity that issues certificates by signing them, which means it uses its own private key to produce a signature that others can verify using the CA's public key. The whole system rests on the idea that you already trust certain CA certificates, often called roots, and you treat signatures from those trusted roots, or their delegates, as meaningful. This trust is not purely technical. It is also a policy decision implemented in software, such as the set of root certificates included in an operating system or application. If a trusted CA makes a mistake or is compromised, it can issue certificates that appear valid to many systems, which is why CA governance and security are so important. In practice, PKI is a blend of cryptography and institutional trust, and you always need both pieces for the system to work. This is the first place where beginners see the uncomfortable truth that cryptography cannot replace judgment. It just helps enforce the trust decisions you already made. Trust chains are the mechanism that lets a widely trusted root delegate certificate issuance without using the root private key for every transaction. Instead of having a single root sign every certificate, roots usually sign intermediate certificates, which are then used to sign end-entity certificates presented by servers, users, or devices. When your device validates a certificate, it is often building a chain from the presented certificate up through one or more intermediates until it reaches a trusted root in its store. Each link in that chain is a certificate signature check, plus a set of rule checks that ensure each certificate is allowed to sign the next one. This chaining enables scale and operational flexibility, but it also introduces complexity because validation must correctly evaluate multiple certificates, each with its own constraints. A useful mental model is to think of it as a set of endorsements, where each certificate says, "I vouch for the next certificate in line within specific limits." If those limits are ignored or misunderstood, systems can accept chains they should reject. Validation is where PKI becomes real, because it is the process that turns a certificate file into a trust decision. When a device validates a certificate, it checks several things, starting with whether the certificate is within its valid time window and whether the identity in the certificate matches what the device expected. It also checks that the chain is cryptographically sound, meaning each signature verifies and the chain ends at a trusted root. Beyond that, it evaluates constraints, like whether the certificate is allowed to be used for server authentication, whether an intermediate is allowed to sign in certificates, and whether the chain violates any policy rules. If you've ever seen a certificate error that mentions name mismatch, expiry, or untrusted issuer, those messages are often simplified descriptions of which validation step failed. The key beginner insight is that validation is not one check, but a set of checks, and different failures mean different risks. Sometimes a failure is a serious warning of impersonation, while other times it is a misconfiguration or an expired certificate that mostly signals operational neglect. It's also important to understand what systems are actually matching when they compare identity. In many common secure web scenarios, the identity in the certificate is tied to a domain name, and your device compares that name against the name you intended to reach. If the certificate was issued for a different name, the device treats that as a red flag because it could indicate you were redirected or intercepted. This name matching has rules that can feel picky, but that pickiness is what blocks a large class of impersonation attacks. Beginners sometimes assume that any certificate from a trusted CA is fine for any site, but that is not how the system is designed. The certificate's identity scope matters, and it is intentionally narrow because trust needs to be specific rather than generic. When name matching is loose, attackers gain space to trick users into trusting the wrong endpoint. So in practice, the certificate is not just saying I am trustworthy, it is saying I am this specific identity, and the validator must confirm that the identity is the one you expected. Another practical dimension is certificate lifetime. Because time is a control in PKI, certificates have not before and not after dates, and those dates limit how long a certificate should be considered valid. Shorter lifetimes reduce the damage window for some kinds of mistakes and compromises, but they increase operational pressure to renew certificates reliably and frequently. Longer lifetimes reduce renewal churn, but they also create longer periods where a stolen private key or an improperly issued certificate remains useful. This is one reason automated renewal systems became popular, because they make shorter lifetimes more manageable without requiring constant human attention. For beginners, the deeper lesson is that PKI assumes change over time, and it uses expiration as a built-in safety lever. Expiration is predictable, while compromise is not, so good operations treat renewal as routine and treat unexpected certificate failures as incidents worth investigating. Revocation is the mechanism meant to handle the unpredictable case, where a certificate should stop being trusted before it naturally expires. That might happen because a private key was stolen, because a certificate was issued incorrectly, or because an intermediate issuer was compromised. The idea sounds simple. Mark the certificate as revoked and have validators reject it. In practice, revocation is difficult at internet scale because validators need a reliable way to learn revocation status quickly, and that learning process can fail due to network issues, performance concerns, or policy decisions. Two common revocation approaches are Certificate Revocation List, CRL, and Online Certificate Status Protocol, OCSP. CRL is like a periodically published list of revoked certificate identifiers, while OCSP is more like asking a status service about a specific certificate. Both approaches have trade-offs, and both can be undermined if systems do not check revocation consistently or treat failures as non-fatal. The phrase revocation reality is important because many systems prioritize connectivity over strict revocation enforcement. Imagine a validator tries to check revocation but cannot reach the CRL distribution point or the OCSP responder due to a network hiccup. If the system treats that failure as a hard stop, legitimate users may be locked out of services whenever revocation infrastructure is unavailable, which creates a strong incentive to implement a softer behavior. If the system treats the failure as a reason to proceed anyway, attackers might benefit because a revoked certificate could still be accepted when checks are unreachable. This is the uncomfortable balance between availability and security, and different environments make different choices. For beginners, the key insight is that revocation is not guaranteed to work the way you expect unless the environment is designed to enforce it strongly. You should treat revocation as valuable but imperfect, and rely on multiple layers like short certificate lifetimes and strong issuer hygiene to reduce reliance on perfect revocation checking. Chain validation also intersects with revocation in a way that can be surprising. It's not just end certificates that can be revoked. Intermediates can be revoked too, and when an intermediate is revoked, it can invalidate large numbers of certificates that chain through it. That is both a powerful safety tool and a major operational event, because it can cause widespread outages if many services rely on that intermediate. This is why organizations and ecosystem operators treat intermediate control with extreme care and monitor for misissuance events. It also shows why it is dangerous to think of PKI as static. Trust relationships can shift quickly when revocation decisions are made. From a learner perspective, this is a great example of how PKI is an ecosystem, not just a file on a server. When a trust anchor changes state, many downstream systems feel the impact immediately or during the next validation cycle. This is part of why certificate-related incidents can feel sudden and widespread even if only one part of the chain was affected. Another practical issue is the trust store, which is the set of roots and trust rules your system starts with. Different devices and applications can have different trust stores, and even the same platform can change its trust store over time through updates. This means two people can visit the same secure service and get different results if their trust stores differ, or if one platform distrusts a particular route that another platform still trusts. That can be confusing for beginners because it makes trust feel inconsistent, but it is a direct result of trust being a policy decision embedded in software. Trust stores also have to handle the reality that some routes become untrustworthy due to compromise or misbehavior, and removing or limiting trust is one of the primary ways the ecosystem responds. This is why staying updated matters, because updates often include trust store changes and validation behavior improvements. When you see certificate errors, it is sometimes the system doing its job by refusing to accept an issuer that no longer meets trust standards. It's also worth connecting PKI to transport layer security, TLS, because that is where many learners encounter certificates most often. In a typical secure connection, the certificate helps the client authenticate the server, and then cryptographic negotiation establishes keys that protect the session's traffic. The certificate is not usually the thing encrypting your data directly. Instead, it enables the secure establishment of session keys and proves you are talking to the right identity. If the certificate is invalid, the system cannot safely complete the trust step, so it warns you because continuing could mean you are connecting to an imposter. This is why certificate problems are often treated as serious warnings rather than minor glitches. At the same time, not every certificate error means there is an active attacker. Sometimes it means an expired certificate, a misconfigured name, or a missing intermediate certificate. Understanding which validation step failed helps you interpret whether the risk is likely impersonation or likely operational mismanagement. A final practical point is how humans interact with PKI, because humans are often the weakest point in trust decisions. When users are trained to click through certificate warnings to get work done, they are being trained to ignore a security signal that was designed to stop impersonation attacks. When administrators treat certificates as annoying paperwork rather than identity control, they may reuse keys, delay renewals, or accept weak issuance practices that increase risk. Even naming choices can matter, because confusing or overly broad identity patterns can cause misunderstandings about what a certificate actually covers. PKI works best when people respect that a certificate is an identity credential, not just a checkbox for turning on encryption. For a beginner, this means you should treat certificate warnings as meaningful, ask what trust assumption failed, and avoid habits that normalize bypassing trust checks. Good PKI hygiene is not about memorizing jargon. It is about maintaining the integrity of identity signals. To wrap this up, PKI is the practical trust framework that allows systems to validate identity at scale by using certificates, signatures, and trust chains anchored in trusted roots. Certificates bind public keys to identities. Chains connect those certificates to known trust anchors, and validation is a multi-step process that checks time, identity matching, signature integrity, and policy constraints. Revocation exists to handle unexpected compromise. But revocation reality is that checks can be inconsistent or softened for availability, which is why shorter lifetimes and good issuance practices matter so much. Trust stores and ecosystem policy decisions shape what your system accepts, and those decisions evolve over time as issuers gain or lose trust. When you understand these moving pieces, certificate failures stop feeling like random breakage and start feeling like predictable outcomes of specific trust checks. Most importantly, you gain the ability to reason clearly about what a certificate really tells you, what it does not tell you, and where the remaining risk lives when you rely on PKI in the real world.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit DailyCyber.News.